Hi guys. So, here's me. My name is Jacopo. Here you have two of my contacts. I'm a Linux kernel and embedded software engineer. I'm currently working with the members of the Linux kernel team. And a few years ago, I started working for a company that was producing barcode scanners. Barcode scanners nowadays are actually black and white cameras. So that was the first time I faced the problem of capturing images, and I realized I didn't know a lot about this. Because image capture, it's not just a software development problem, it ties into theoretical knowledges that are not that widespread. It has very specific buses that are used just for this part. And if you're doing that on embedded systems, it's even worse because you have dedicated pieces of hardware that usually are black boxes and you don't know how to handle them. So 2 years ago, I would like to add a presentation where I could have pointers to start looking into that, and I hope that this presentation will give you exactly this thing. But that means that you already know about image captures and related things. You will be getting bored for the next hour. Sorry about that. So I will start with an introduction about light, colors, and pixels, and let's see what an image sensor is after that, how images are transmitted from the sensor to the SoC, and a brief introduction about video for Linux, which is the framework for dealing with image capture on Linux systems. So let's start by saying that color is not an absolute value. Color is a perception, actually, or a physical phenomenon, of course, but that means that it's hard to measure that. So if this is the electromagnetic field, so we only see a tiny portion of that, which is this one. This is the visible light spectrum. And not human animal species perceive color the same way, because, again, that's a reaction to physical phenomena. So it turns out that humans are actually as a trigonometric view, so we mostly see three colors, which are the blue, green, and red that corresponds to medium, short, and long wavelength. And since we live in a digital world and we want to transmit and deal with colors, we need a mathematical model to correlate a perception of the physical phenomenon to the photooptic property that triggers it. So a light beam that we perceive as a single color is actually composed by several components, each one with a specific wavelength. The way it is described usually is that if you take each component and everyone with a specific wavelength, and you plot the value of specific photooptic properties like lighting power, that depends on what you're measuring, you got what is called the spectral power distribution, which is that graph over here. It's interesting because sometimes colors that are perceived as the same color are actually different if you look at the spectral power distribution. But we know that, let's say, particle has these values in function of the wavelength of the components of the light beam. So as we see basically three colors, the most simple way to find a correlation between the spectral power distribution and numerical value is to sample in correspondence to blue, green, and red the value of the photooptic property we're interested in. So if we want to describe particle in mostly unique way, we can say that this is just the value of blue, this is just the value of green, and this is the value of red that gives you particle. The same goes for all the other colors. So in this way, we have constructed a mathematical model that is nothing more than a tool, but describes unically with a tuple of value, the color, the perception of the color. We can call that the long, medium, short color space, but again, that's a tool. So in 1931, a committee, the CIE, I think they made an experiment with 18 people, that's not a huge number, and defined what is called color space, not the proper mathematical definition of color space, which led to the definition of the two main color spaces that are used today, which are the RGB color space and the XYZ color space. RGB uses the primary color to define all the other possible colors, while XYZ uses Luma components and chrominances. That's because we are sensible to these three colors, but the human eye is even more sensible to changes in brightness. So we can define a color as the brightness and to associate with chromancies, and on top of that, other color spaces have been defined, which are known as sRGB color space, which is the one used usually in digital electronics. Adobe RGB, which I'm not sure where it is used, but it's a thing. CYMK, you may have seen that for printers. Anyway, each color space has its preferred way to be used. So on top of color spaces, because things are confused here as naming and things, there have been those kinds of color encoding schemes, which are based on the same color space, but are mathematical tools to move from one color encoding to another. So we have the RGB color encoding based on the RGB color space, and we have the mathematical tool, which are usually matrices, to move from RGB to, let's say, YGRGB. And we can do the transformation back and forth every time we want. So names are confusing because we have a color space that is called sRGB, we have a color encoding scheme that is called RGB, we have YCRCB as another color encoding scheme, and we can build more things on top of that. So we now have a mathematical model that we know we can use to represent colors and digital values. And we can now look into what is the most basic components of an image, which is a pixel, which is, I'm sure you know what it is. So, but we should ask ourselves, if we use three digital values to represent a single pixel, which is the bandwidth required to transmit an image of this size, which is not used for nowadays application? It turns out the bandwidth required is quite high. So for an image of that size, we will need 24.5 megabits, and that's not a good thing, because that means that we would need very high bandwidth buses, and things get complicated. So it's highly impractical to sense all three color components for each pixel, because we would have huge sensors with a lot of points, and that increases the production cost, require a lot of bandwidth. So we need some improvement from that moment. It turns out that there is a thing called biofilter, which is kind of a simple idea, because if we put a large filter on top of each pixel will sense just a single color channel. So if we have a matrix like this one, the first pixel in the matrix will just be green, the second will just be red, and we have various things that we can use to create now the biofilter. We of course need a way to reconstruct the full pixel value, the full pixel color from the single information, and there are various schemes for doing that, the mosaic, interpolation. The idea is quite simple, that because you're using the information from neighbor pixel to reconstruct the value. So if the first pixel is red, transmit the red channel information, you can use green from this one, and blue from this one, to reconstruct the color here. The same goes for the other one. There are more smart schemes for doing that, this one like this one. Anyway, you got the concept. So now that we know how we transmit images, this is what a sensor integration looks like. So we have a sensor that wants a clock toward, and this simply usually have a communication interface with the SoC and a data bus that is used for transmitting data. That what it's inside an image sensor, and it's exactly the same thing. So you would have a communication interface here that's usually S4C, and it's used to send messages and program the registers in the sensor. The way the registers are programmed influences the way the images are transformed. We'll see that later. We have here the timing phase generation, which is kind of important because if you are transmitting an image, you have to find a way to tell the receiving part when a frame starts, when a frame ends, when a line starts, when a line ends, what is the pixel output clock frequency, and those things are called time generation part. So you actually have here the image array This is the photo-optic receptors with filters on top, so it's a barrier filter. And the raw images, which is called the raw matrix, goes through what is called the analog processing part that makes the transformation of different color encoding schemes that are the ones that we program using this register. Depending on how smart is the sensor, you can have advanced feature here, you can have DSPs that perform transformation, advanced algorithm like auto-white balancing, auto exposure, and things like that. So again, this is called the pixel grid array. That's the grid. It's a grid of photo-optic receptors with filters on top, and we can ask the sensor to, starting from the raw grid, to give us a specific color encoding, like let's say, here it is, permutation of RGB, YUV with different subsampling. We can ask the image sensor to perform manipulation of the image, so cropping just part of the image, downsizing that using binning, so skipping some lines, and giving us back an image with lower resolution. We can zoom on the sensor, asking to just giving us a part of the image, that's a zoom. And again, depending on the sensor capabilities, we can have more advanced features like, let's say, 3A, mirroring, flipping. I'm sure there are sensors that do very advanced things nowadays. So we know how images are transformed, and now we want to know the way that how they are sent and transmitted to the SoC. So basically here we have two kinds of buses that fall in two different categories, which is the parallel buses and the MIPI-defined serial buses. Parallel buses are the one that is older, it's cheaper, it's used to poke into with that with scopes and probes and whatever to do. You can do that on your desk. You don't require advanced hardware for doing that. Of course, you would find this here in hobby design, older design, because the performance are poor compared to newer buses like this one. MIPI is a standard committee, has defined a set of buses for image transmission, display, a lot of things. They are buses with a higher data rate. They are used for modern applications, for smartphones that are transmitting huge images with awesome qualities. It's much more integrated, so it's very hard to use a solder one by hand on your desk. And it's very hard to debug, of course, because you need a protocol analyzer and stuff like that. But that's the kind of standard nowadays. So, parallel bus, they call BT. This is not a standard name that is confusing because BT defines a lot of things, but also defines the bus structure. BT601 or BT656 depends on different things. Basically defines the way images transmitted using wires for synchronization signals and the parallel bus that transmit out pixels. So we have the signals for synchronization, VSyncs, a pulse here tells us the frame is starting, H-sync, a pulse here tells us the line is starting. Or href, that is basically the same thing, that defines when a line is valuable. Here we have data that are actually clocked out on the parallel bus. And that's kind of simple in principle. That's, again, for older and obvious designs. From the other side, we have what is called MIPI CSI-2, which is much more than the definition of just a physical protocol. MIPI CSI-2 defines protocol for transmitting images, describing what we're sending on the bus, and can be based on two different physical layers, and defines a set of image formats that are accepted. So this is much more comprehensive as a definition compared to the single parallel bus. And again, there could be two physical layers that MIPI CSI-2 can use. D5 was the first one. It has quite a high bandwidth per lane, 1 gigabit. It has one clock signal for the whole bus and up to 4 data lanes. C5 is kind of new, but it's very interesting because it's using trials. So that means that the clock lane is integrated with the data lanes. So you have trials of clock and data lanes, and it has a much higher bandwidth. All of these are differential signals that make it even harder to work with other open instrumentation. Again, MIPI CSI-2 doesn't define just a physical layer, defines also the protocol that you use, the protocol built on top of that, and it's a packet-oriented protocol. So you have short packets for synchronization, so you have a special code that say, here starts a frame, and you have another special packet code that says here starts a line. These are called short packets for synchronization, and you have long packets that transmit data. Data are described by the packet headers. Then packet headers can be transport other information that are called data type and virtual channel. This is very interesting because it allows you to do interleaving on different image streams using the same physical bus. So data type is defined by CSI-2 specification and defines which kind of data the packet transports. Which kind of data in terms of which kind of image encoding or which kind of metadata you are transporting. Virtual channels instead are just simple numbers that goes to 4 available one in the previous set of specification, now it's 6, and allows you to interleave different streams on the same physical bus. Of course, you can have data tape interleaving on top of virtual channel interleaving. So if you take a simple use case, you can think about a sensor that transmits capture images, and along with that produces metadata. Metadata tells you, let's say, the exposure time used to capture an image and other details. The sensor interleaves them on the physical bus using data type. So you will have a long packet of data, short packet, let's say, here starts a frame, short packet of data which is actually images, short packet of data, a long packet of data that says this is metadata. And the receiving side knows using data type how to handle that, how to split them and present them in different places in user space, user space. If you put that on top of virtual channel, things can get complicated. So I don't want to go into detail of that, but the basic idea is that you can have multiple sensors or the same sensor producing more data type, more different data that are more multiplexed on the same CSI-2 bus. All of that is enclosed in its own frame start, frame sequence, and its own is defined by a virtual channel identifier. So what happens is that you have the same sensor you had before. Maybe the same sensor can produce what is called preview images. Usually you have capture images, which are used when you actually take a photo. It's very high resolution. It's a lot of data. When you are using a mobile phone, for the viewfinder, you want that to be snappy, you want it to be reactive, and it's usually lower resolution data. Also, you can have things like that flow. All of them can be interleaved on the same bus. In a specific frame start and frame end, and things can get very complicated. The good thing here is that usually on the receiving side, using the virtual channel, again, can split data information in different memory locations to present them to user space as different images. So it's bad, but not too bad. So far we've been talking about images, we've not been talking about software, and we've not been talking about Linux. And when you're dealing with image capture, usually the framework of choice is of course needed for Linux, that defines a set of interfaces from the user space and the driver-to-driver communication for capturing data, image data. So that's the simplest possible architecture you can have with video for Linux infrastructure. So starting from the hardware, you have what we had before: simple sensor, a receiving side, and FQC bus to control the sensor. On top of that, you build your platform-specific data. This is the receiving side, and the sensor driver data that drives the sensor using FQC messaging. On top of that, you have what is called the virtual Linux core that has helper components that you can use from your driver to do things that are shared between drivers, and defines what is the user space interface that you use to control the word capture instruction. So when you start, if you want to capture an image from that using video for Linux interface, the first thing is that you will use the most basic interface, that is video device interface, and you open that and you start calling IO control from that. IO control that I usually, initially you should grab a sensor to know which kind of data you can transmit, if that fits with what you're expecting. And you can set a specific format on the sensor and on the platform. You set the image size because you have to be sure that the image size is when you capture the image. And you can control streaming parameters like the frame rate, the exposure time of the sensor, using a set of IOCTL that is defined by video parameters. There is a huge problem. We are transmitting big data between on the bus. So, and we need lots of memory for doing that usually. And we need memory with special requirements because we need memory that is DMA capable, of course, because you don't want the CPU to be involved in transferring data from the receiver buffer to the main system memory. You would like to have DMA capable memory that is usually contiguous, because otherwise you would have to have a DMA engine that supports scattering and gathering and assembling memory together. This is not that common. You would like to have memory that's still accessible by the CPU and the device, because one is writing, the other one is reading, they have to be coordinated. And possibly, if you're writing high-performance application, you don't want to have memory, to have user space involved in moving memory from one side to the other. So you want to share memory between different subsystems. So there are, video for Linux defines three possible memory allocation models. The first one is that the user space allocates memory and passes down to the driver. This is rarely seen today because it's very hard to make assumption of memory with where user space allocated memory it actually is. So you can have memory that is split between different locations, and then you go back to the problem that you need scattering data in your DMA engine. Or you can have the kernel driver allocating memory for the user space and the user space memory mapping on top of that. Or if you want to have very performant application, you can use the DMA buffer structure to share memory between different kernel subsystems. So in case of mmap, memory allocation, simply you issue a request bus IO control that goes down to the video for inductor. It has a part that is called video buf2 that uses the DMA API to allocate memory for you in DMA capable network. After that, user space simply has pointers that it can map and access that memory from user space. Otherwise, you can use DMA buf API and have another subsystem allocating memory for video for Linux. And that subsystem will act like the memory exporter. That means that it can export memory as DMA buf descriptor that are integers, so you can think of that like file descriptors. And you issue an I control here, and another IOCTL control here, and that's simply provide those file descriptors to video for Linux core. In this case, video for Linux is not. In this case, video for Linux is not going to allocate memory for you. Instead, it's going to point to the memory that's being allocated in another subsystem in the random example. So after that, you can start using this what is called the streaming API to actually stream image capture from one system to another using zero copy, because the memory is placed all in kernel space. You don't have user space involved in that. So all platform drivers have a queue of available buffer location where they can store data, and you simply queue a buffer to your driver, which you make them available to your driver, and that makes it point to the memory location that is being allocated, let's say, in your end. You do that for all your available buffers, and you actually start streaming. Start streaming means that the sensor driver will send a message to the sensor that says, okay, you can start producing data, and data will flow in this direction. Of course, when you do the star streaming thing, you mean that you are pointing your capture drive, the DNA engine of your receiver to the buffer that is being rotated here. The user space here waits using this control for data to be available, and when after a while you will have the first frame that will be captured, you will receive an IRQ here that says, hey, you have memory, you have data available here. So this simply unlocks user space. User space knows that there is memory here, and it can produce what, let's say, an atomic, I don't remember the name for DRAM, but it can update the DRAM to display the image that is being provided by this atomic MOS. So you can repeat that, you can go on and continue that until you stop streaming, and you simply have to realize an application that capture images for DRAM display them without involving user space at all, using the MIPI API. Okay, so basically we've seen we have a platform driver that controls the receiving part of the SoC, and it is in this directory here. We are the responsibility. They transfer images from internal buffer to the system memory, and with all the constraints we have said. It can transform images, perform transformation of images. The hardware has capability for doing that. We will see that later. And implement the user space API that are not part of the framework, and allows the user space to control the streaming operation. As well, we have sensor drivers that install in this directory and controls the sensor through I2C messages. It's pretty interesting here the fact that image sensor producers do not like you to control exactly what happens on the sensor. So you receive a long list of register values, pairs, and you simply write them to the bus, hoping that everything works, and tweaking one of them at a time, hoping that you're not breaking anything. So it's kind of a painful procedure, but that's the way this one was produced. Another interesting thing is that we're talking about embedded, so we're talking about usually ARM processor, and we're talking about device tree. So if you have seen the previous talk, Mark gave a nice description of what the device tree is. The device tree is nothing more than a textual description of the system that gets compiled to a binary block. And the Linux kernel just starts parsing that, instantiating driver for each node in the tree that you need, that you encounter. Each node has parameters that are back to a driver, and the driver is expecting to see them in a certain code, and that's defined an API between driver and device. The video devices have very specific device tree bindings, which are described in this directory. There is a video interface, .txt file that describes the general bindings for all video interfaces, and describe, most importantly, how do they connect to each other. So this is very simple representation of a possible device tree for a video capture device. So you will have a set of ports. Each port effectively corresponds to a physical input in your SoC when you're receiving side. And each port has an endpoint, which instead describes the specific input through a set of endpoint point properties. And that this abstraction that is called the remote endpoint that points to the P handle, which is nothing but a reference to another device tree node of what is instead the sensor driver, let's say. So in this way, you are describing a physical connection between the receiving side, the SoC host, to the sensor, to the driver, handling the sensor. So we said that there are endpoint properties. They are bus specific usually, so you have a set of properties that are specific to parallel bus. That says let's say, what is the polarity of the distinct, because you have to know that, otherwise it will get messy. How many data lines you have, what is the polarity of the active edge of pixel clock, and things like that. And the same way, you have specific property for CSI that describe the frequency, how many data lanes you have, how are the data lanes organized, and things like that. And it's very interesting that there is a framework ending those kind of properties that it's the different to async framework and different to firmware framework. So this is a typical probe sequence of a video capture driver, and what you do the usual things: you create memory, you request interrupts, you deal with power management, and this is very platform specific, depends on what the hardware does, but there is a part that is quite common, that is the DT parsing part. During the last 3 parsing, you basically walk over your endpoints and collect references that we have that represent the sensor your SoC is connected to. Once you do that, you use those PNL to register a notifier that waits for those sensors to be available, to be probed. It's set to be async because there is no guarantees that your platform drivers probe before the sensor driver, so they can get confused. And you use that framework to register notifiers that waits for all of that to be available, and once they are, the driver knows that the user space can start calling function that and actually use the video capture interface. So this is the very most simple use case you can have. This is just a sensor, a receiving side, nothing else, that take data, write them to memory, user space patches them, and do whatever you want. This is not the case with today modern SoC, because modern SoC have very specific blocks for performing image transformation and performing images manipulation that in a way that is way more efficient than what an image sensor can do. So the video device node abstraction is not enough for that, because you have a single point user space where you are meant to control all the SoC components that can do image transformation, things that it's limiting. And so there is a new set of API that is called the Media Controller API that allows you to do that. Media Controller API describes the hardware as a set of entities, each one with specific properties and a set of sync as the source file, then can be connected in order to form an image processing pipeline that happens on your SoC. So this is more likely what a modern SoC looks like. So you have the hardware part here, which is similar to what we had before. So you have a sensor and you have a receiving side. But on your SoC, you don't just have the receiving part. You also have what could be a resizer, a pixel formatter, pixel converter, whatever your SoC provides. They can be very nice features. And of course, you can have different paths between all of them. That ends up in system memory or in write-back buffers, because maybe you want that to be sent to the resizer again. That's, again, very platform specific. Of course, that needs an abstraction, the user space, that is the abstraction that provided by the Media Controller API, where each component is described by an entity, and entities can be linked in this way to perform to realize image transformation pipeline like this one, which applies to the hardware, setting the hardware in the proper way for performing image transformation as image are captured. At the same time, you may have a very simple use case where you don't want to use all the things here. So the Media Controller API allows you to link the just the receiving side to the main memory and perform to node transformation. That's all it is. So it's interesting because this complexity here is represented, implies more complexity over there, of course, because now you have to control the format and the sizes and other parameters of each node of the pipeline. So this requires a completely new set of API that is called the subnet API compared to the device node API. So this is an extension that is painful to work with, very powerful, but require user space to be aware of each single component, which format it supports, which format has to be configured in each of these entities, and how to link them. But you can have very powerful things. You can maybe have a sensor that produces this kind of data. This is why you default it to this resolution, and you want to pass it to a resizer because you want it smaller. You want to convert it because maybe you want NV12 or NV16 or another memory format. implemented in a specific way before presenting it to user space. To do that, you use the FOSDEM API, and you go to each entity here that has a user space representation, that's called reader subdevice. And on the reader subdevice, you set format on each source and sync file in a way that reaches out to the pixel to the size to the pixel converter. That you're going to receive data in this format, but on output, I want this format. The same goes for resizer. Let's say you're going to receive images with this size. You're going to output images of this size. So the end result is that you have configurable pipelines that exploit the hardware feed, the hardware capabilities of your SoC to perform image transformation, and you control that to user space. So, of course, this implies more computation because system usually boots your system in a way that is not usable because the pipeline is not, sometimes it's not available, and you have to create that. So you cannot just move the system and start fetching images. You have to have a user space utility that controls that and set it up. The reader device API and reader device subdevice API share a lot of things, but not all of them. So it's kind of hard for user space to control that in a way that is unique between the two, and you need to be careful doing that. And sometimes you just want to capture images. You don't care about doing transformation because let's say you have a very simple use case. You want just to receive images in the format that the sensor can provide them. So you have to link the thing to completely skip the pipeline, and all this complexity sometimes not justified. So this is, I think I've been too fast probably. No, it's good. So I hope you have questions now because we have plenty of time. So here. Go please. Yes. Okay, so the question is that how do you compare video for Linux with OpenMux? So OpenMux, if I'm not wrong, is a standard defined by the Kronos working group that defines lots of different things, and I'm not an expert on that at all. My understanding is that OpenMux defines things that are does more things than video for Linux. My understanding is that it does something that is in between video for Linux and distributor, because it allows you to do the creation of more complex pipeline with things like transmission of images through the network, I guess, something like that. I cannot tell because I don't know OpenMux enough. Video for Linux is more tied to the kernel space and early user space API, while OpenMux allows you to create much more complicated pipelines. Of course, this is less common in the Linux system, from my understanding, but also is multi-platform. So I guess that's drawbacks, but it does not receive that many support for many kernels as part of the understanding. So please. Okay, so the question is that are those, I think they're referring to the media controller API, are using modern SoCs and Android systems like mobile phones. So Android is a weird beast from that point of view. If you think, if you're asking about general modern SoC, I would say yes, of course. If you're asking me specifically about Android, it's a weird beast because everything, you see producers that are making chips for Android phones think that there is a lot of value in what they're doing in hardware side, and they don't do like that much to do that in the space. So you see very weird abstraction to move the thing from kernel space to user space, like driving that just take loads of register and write them to the hardware without knowing what we're doing, and those are coming from user space. So you're seeing weird APIs that do not match exactly what they reader for Linux support. So I cannot tell if that's a reader for Linux drawback or vendors being ignored in that, not ignored, being not good citizen of the open ecosystem doing that. But yeah, so modern SoC of course. Android is another beast. But I hope that there exists Android implementation from the SoC that you fully use the media controller API. So the question is, what about OpenCV that runs in user space and can maybe exploit some feature of the SoC? So I know very few things about OpenCV, so I don't know if my answer is useful here. My understanding is that OpenCV is a consumer of this kind of API because they receive images, and they may have some, let's say, media controller support not only capture devices but also memory-to-memory devices. It will fully support codecs. And so I think that OpenCV as an implementation of using media controller to exploit the feature of the SoC for using things like memory-to-memory transformation, that's what we would have what is called the hardware acceleration in that case. So I cannot tell what is the status right now with supporting that with OpenCV, but let's hope to anyway that's the case. Thank you, Joe. Questions?
Yes, so you have to typically do CSI-2 virtual channels, and they have a different resolution, and how does that work?
Well, on the hardware side, yes, of course, because you can do mixing of different streams with different. I may try to go back to the slides here. Yes, it is quite a long time. Here. So here, maybe I'm not being clear enough on that, but those streams here are completely different streams. So one is may have a lower resolution because you're using that for viewfinder, while when you touch the take picture things, you want to have an image with high resolution. So they can be interleaved without, ground constraints that are defined by this MIPI CSI-2 specification. But there is no connection between what kind of data you have here and which kind of data you have here. So you're free to interleave different resolution, different image sizes, different data terms that this is images, while this is metadata, this is text usually. Or this is depth not. This is a map of points of text. You are not tied to specific images or resolution or formats. By intermediate streams. Access the data from kernel space? Yes, but if you're accessing from this streamer, you already presented that to the user space. So you yes, the DT, the data type, it's used exactly for that. So the receiving side knows how to split data using the data type. So they know how to direct. You can have two different video device nodes in user space. One gives you image data, the other gives you metadata. Then you have a completely different set of problems, that is how you keep that in sync. But that's another problem, that's a different thing. But yes, they are used exactly for this reason. Split images different video node and then presented to user space from different perspectives. So different data and different video. Anyone else? Mark again. So that's the example with the mmap. That's the thing here, right? Oh, OpenGL. Well, I don't know that much about DRI. So I think OpenGL stands a bit here, a bit upon this one. This is the DRI framework, DRI Direct Rendering Manager, that implements the mmap API. So if your driver complies with the mmap API, so it's part of DRI, you can ask them to export memory as mmap descriptors. I'm not sure if OpenGL is involved in that. I think it's a layer on top of this. Isn't that? So I cannot actually. Yes? Say again? Yes. Okay. Yes. There are many platforms for that. I can, of course, manage Kubernetes associated that have it's ongoing work to have the mainland that is fully open source implementation. I think the OAuth 3 and LSP does that. If I'm not wrong, 316. Not 316, INX, that was 316. As an implementation for that. Well, again, all drivers in MIPI, I think that's a way for doing that, and most of them, if not all, support media controller. Some of them support media controller. I cannot tell why on Raspberry Pi you would need something like that to buy anything. Maybe they have a different type of media. Someone asked about OpenMux. They choose to have to support OpenMux instead of beautiful links to have binary driver that runs of microcontrollers, and you can control them with a set of RPC code within the SSD command controller, and you need binaries to run them that runs on the microcontroller and implement all the RPC for that. But that's I don't know why something like that. But yes, right implementation that we realize that are doing output. Other question? Okay, so I would like to close thanking my colleagues, colleagues and people who have been working here last year, because I started knowing nothing about that, and there's been no